How can inertial navigation determine its location without relying on GPS? But why is it that the longer an inertial navigation system operates, the more prone its position is to drifting? In just 3 minutes today, I'll explain in plain language how inertial navigation error compensation algorithms actually work. Let's start with the fundamental principles of inertial navigation. Inertial navigation relies primarily on gyroscopes and accelerometers to sense motion. Accelerometers measure acceleration. Integrating this once yields velocity, and integrating it again yields position. That is precisely the problem. Sensors cannot be absolutely accurate. Even a minuscule measurement error will accumulate continuously after 1 or 2 rounds of integration. Therefore, inertial navigation systems have a very typical characteristic. They are highly accurate over short periods, but the longer they operate in purely inertial mode, the greater the error becomes. So, where do these errors actually come from? They can be broadly categorized into 2 types. The first type consists of errors inherent to the device itself. Examples include bias, scale factor errors, installation errors, and random noise. Simply put, the device hasn't actually moved, but the sensor registers a slight movement anyway. If it actually rotates by 10 degrees, it might measure only 9.8 degrees, or the 3 sensor axes may not be mounted in perfect orthogonality, leading to error crosstalk between the axes. The second category consists of dynamic errors generated during motion. Examples include coning error, sculling error, and scroll error. These names sound rather complex, but the underlying principle is not difficult. When aircraft, missiles, drones, or ships undergo high-speed rotation, intense vibration, and rapid maneuvering, discretely sampled data cannot perfectly reconstruct the actual continuous motion, resulting in additional computational errors. So how do we solve that? There are 3 main approaches to inertial navigation systems. The first is calibration and compensation. Before the product leaves the factory, the inertial navigation system is mounted on equipment such as a high-precision turntable and subjected to known motion. The true values are then compared with the sensor measurements. This allows for the calculation of parameters such as bias, scale factor, and installation errors. These error parameters are then programmed into the compensation model. Simply put, first, identify where you went wrong, then subtract the error in advance. However, calibration cannot solve every problem. Temperatures fluctuate, components drift, and the motion state of the carrier is constantly changing. Therefore, real-time algorithms are also required to continuously correct dynamic errors, such as coning errors. The second method is called rotational modulation. The concept behind it is highly ingenious. Instead of directly eliminating the error, it allows the error to cancel itself out. By rotating the inertial measurement unit according to a specific pattern, errors that would otherwise have a fixed orientation are made to vary periodically within the navigation coordinate system. After a complete cycle, some constant errors can cancel each other out. Therefore, rotational modulation is commonly used in applications requiring high precision for long-duration, pure inertial navigation. The third type involves integrated navigation and intelligent algorithms. The most typical configuration is inertial navigation plus GNSS plus Kalman filtering. When GNSS signals are normal, the GNSS position and velocity information is used to continuously correct inertial navigation errors. When GNSS fails due to tunnels, underground or underwater travel, or signal interference, the inertial navigation system takes over to maintain precise positioning. Now, however, deep learning is also beginning to incorporate error compensation. By learning error variation patterns from historical inertial navigation and GNSS data, velocity and position errors are predicted and corrected following a satellite signal outage. Therefore, the true high precision of an inertial navigation system does not depend solely on the sensors themselves. While high-performance sensors determine the initial level of error, calibration, compensation, and fusion algorithms determine the extent to which that error can ultimately be controlled. From factory calibration and dynamic error compensation to rotational modulation, Kalman filtering, and AI prediction, inertial navigation technology has always addressed one core problem: how to keep a system that is inherently prone to drift accurate for as long as possible.